Welcome everyone to today's webinar, Transform MongoDB Data for SQL Applications. This is Marlis Furs coming to you from the Progress Data Direct Studios in Morrisville, North Carolina. I'll be your host for today's session. With me in the studio today is Brad Wright, our Senior Principal Product Manager at Progress Data Direct. The topic Brad will be covering is connecting the worlds of NoSQL to standards-based applications such as analytics. I would like to hand today's session over to Brad Wright. Welcome, Brad.
Well, thanks so much, Marlis. And good afternoon, everybody. Thanks for taking time out of your busy schedule during the middle of the week to join us for our webinar today on transforming MongoDB data for SQL applications, and in particular, connecting the worlds of NoSQL data, which is a very hot space right now, to the standards-based application ecosystem of your organizations, such as analytical tools and BI tools. I'm Brad Wright. I'm the Senior Principal Product Manager. So let's go ahead and kick things off. So what are some of the standards-based applications that exist in an enterprise, and what are some of those use cases that require connectivity to data, and in particular to this new class of data, NoSQL, and in particular MongoDB? So there's a number of classes of standards-based applications, and when I say standards-based, when we say standards-based, what we mean is SQL, SQL-based applications that have been constructed and developed and written to consume data using the SQL standard. So those applications are business intelligence and analytics, like I've already mentioned, data integration and data federation type applications for moving data around an organization, or virtualizing data for consumers, things like extract, transform, and load products. Web applications, web applications obviously consume data, and the vast majority of those web applications are currently written to the SQL standard. Business applications that business users use as part of their day-to-day decision-making and business processes, and mobile applications as well. So organizations have spent huge amounts of capital, a lot of money, on these sorts of applications, millions and millions and millions of dollars, and they're all over the enterprise. And the challenge, or as we're going to see, is connecting those applications and connecting that investment of standards-based applications to these new classes of data sources, and in particular MongoDB. So just a quick little bit about who we are for those of you who may not be totally familiar with Progress Data Direct. We are the provider of the largest family of standards-based connectivity, SQL-based connectivity products in the world, and have been in business for almost 30 years, or right at 30 years. Our primary flagship product line is our Progress Data Direct Connect products, which are, again, about providing SQL-based connectors in the form of ODBC, JDBC, or ADO.NET drivers and or providers, these standards, to many different types of sources, which you see depicted here on the right-hand portion of this slide. Obviously, all of the quote-unquote traditional relational data, the Oracles, the SQL servers, the DB2s, etc. Data warehousing products, Teradata, Sybase IQ, Greenplum, Pivotal, and those classes of data sources. And in the last couple years, with the rise of Hadoop, connectivity to products like Hadoop and the various distributions of Hadoop, and our topic today, NoSQL, and in particular MongoDB. So connectivity to standards-based connectivity to this new class of sources that are called NoSQL, and are also sometimes referred to as big data. And also standards-based connectivity to SaaS sources or cloud-based sources like Salesforce or Eloqua, and applications that live in the cloud that this family of, or this investment of standards-based applications, which we saw on the last slide, might also need connectivity too. So that's a little bit about who we are and the business that we're in. So what is MongoDB? We talk about this new class of sources, data sources for storing data called NoSQL. And that name is sort of a hint. But specifically, what is MongoDB? MongoDB is a very popular document-oriented database that provides very high performance, very high availability, and scalability to organizations. And it stores, since it's a document DB, it doesn't store data in rows and columns like we're used to, like most of us are used to with relational products. It stores data as JSON documents. And you see a little snippet of what a JSON document looks like at the lower right portion of this slide. Very self-describing, very potentially deep and complex and potentially very nested. MongoDB as a JSON document store is schema-less and schema-free. What one puts into MongoDB does not have to conform to a well-known schema designed up front, a rigid schema. Data in JSON is denormalized. It's not normalized like we would typically expect from, again, a traditional relational source. There are limits to what MongoDB can do in terms of the sorts of operations that standards-based applications expect to be able to do, like joins. And maybe finally and most obviously, MongoDB and products in similar to MongoDB in this class of data sources known as NoSQL don't have a SQL interface. So the question then is, the pain then is, as organizations adopt these new class of sources, NoSQL sources, and in particular MongoDB, and MongoDB is experiencing very, very, very strong adoption from the largest of the global financial institutions to familiar web scale organizations, all the way down to unknown startups. Organizations across the spectrum are adopting MongoDB because of some of the benefits that MongoDB provides, primarily being schemaless and thus very easy to develop to. But these organizations are making investments in MongoDB, but they've got existing investments in all of those types of standards-based SQL applications that we saw on the first slide. Many times, millions and millions of dollars of investment. How do these organizations, how do you and how does your organization connect these two worlds? Data that's in these new MongoDB systems is obviously business critical data. It's obviously relevant to the rest of the organization and decision makers in the rest of the organization. So how do you bridge these worlds? How do you connect the worlds of NoSQL and standards-based applications, and in particular business intelligence and analytics type applications? So that's what we need. That's what we're here to talk about in our webinar today. So, speaking specifically about MongoDB and JSON document and as a JSON document store, there are existing solutions, existing connectivity providers out in the open source, and some commercial solutions that do provide connectivity, standards-based connectivity to MongoDB. But all of these solutions currently in the market take the approach of flattening the data that's in JSON stored in MongoDB. And that's simple and it's straightforward, but it's really not the natural way that a relational application or a standards-based application wants to see this data, wants to see that data. So if we just, what do we mean by flattening? So let's just look at this example here in this slide. So you see again in the middle a snippet of JSON describing an employee whose name is Brody. That employee has an address in a nested JSON document. That curly brace in there in the middle is sort of an example of how JSON data can be arbitrarily can be nested arbitrarily deep. And this employee has in this JSON document an array of emails, in this case 2 emails. So when we say flattening, what these providers do, they take all of that data, all the individual little data elements in that JSON document, regardless of their depth, and collapse it into one flat, potentially very wide relational row. So in this case, you see an example of that at the very bottom of the slide. So yeah, I've got an ID, and the name is there, and the street address is there, and the city address is there, etc. And these email values are there, and they're all as columns. You know, at first blush, that looks pretty reasonable. But what happens if the document is deeper than this particular example? Or what happens if there's an individual that has 4 email addresses as opposed to 2 email addresses? How would that impact this approach of flattening? What would a flattened approach do in that situation? And that's where this approach begins to fall down, because it results in potentially changing column structures and increased data repetition that really complicates and is unnatural for how standards-based relational applications want to see and expect to see data. So what's a better way? The better way, in our opinion, is the approach that we took with our MongoDB standards-based connectivity, and that is to really what we call normalize that arbitrarily deep MongoDB data and give you and your organization's power over how that potentially deep, complex data is going to be represented in a very natural way for relational consumers. So we provide the ability to look at that data that's stored, that JSON data that's stored in a MongoDB collection, and really make choices about how to represent it in a much more natural second normal relational form. For those of you who are familiar with relational products and know normalization, this is really about providing a capability to represent that data in second normal form, where, again, with that same example that we saw on the last slide that was flattened, pieces of that that employee data, of that employee JSON document, get mapped into an employee table. So in this case, name would get mapped into that top level parent table. Address, street, city, state, that's in that nested portion of the JSON document could be, and in this approach is mapped into a child table, or you can think of it as a sort of virtual table, a virtual child table that represents that nested portion of the JSON document. And in this case, that is called employee address. Again, it looks very much like a relational consumer would expect to see. And more equally importantly, and sort of this is where it really the power of this approach really begins to shine, is nested arrays in a JSON document. In this case, the emails portion of this JSON document. That itself can get and would get mapped, and again in this example, into a separate virtual child table, in this case employee emails, and array elements that are in the JSON document, that portion of the JSON document, now are represented as rows. And that's exactly what a relational consumer would want to see. Because if the next document in this collection, the employee described by that document, that individual has 4 email addresses, they would have 4 rows. So this relational view into this potentially arbitrarily deep, complex, and changing JSON document is stable and is natural for a relational consumer. So that's the approach that we provide. In addition to flattening, there certainly are cases where flattening, there are examples of JSON documents where flattening does make sense and is the right approach, but there are many, many cases where it is not the right approach. And what we've seen in the market are organizations take and do sort of sort of unnatural acts to their JSON document to make the data in their MongoDB collection sort of fit into that flattened approach when they're using some of those other options that are available in the market, when in reality they need an approach that supports both flattening and normalization. So what are some of the benefits of normalization and our approach to normalization for connecting the worlds of NoSQL to standards-based applications? Well, in this case, one of the benefits is it exposes complex MongoDB data using concepts familiar to SQL practitioners and familiar to SQL-based applications, rows and tables that, parent tables and child tables and foreign keys and primary keys and relationships between tables. These things are familiar, right? The vast majority of applications and individuals inside our organizations today are familiar with these things. As JSON arrays grow, the table, the view, that relational view of those table definitions, both parent and child, remain constant. We saw an example of that on the last slide. One row, one individual is described by a document that has 2 emails. The next individual is described by a document that has 4 emails. The next one has 6. And that view, that relational view is stable because those array elements are represented as rows, not as columns. And a flattened approach would have to potentially change and add columns. And changing table definitions are certainly something that standards-based applications do not expect frequently. Simpler and narrower table definitions to represent complex JSON. So again, you don't have this big, wide row. You've got something that makes sense and is frankly just much easier to consume for SQL practitioners and applications. And that model, this normalization model, supports joins in a natural way, and in a way that can still be optimized into a single MongoDB query or interaction. So SQL practitioners and SQL applications like to do joins, and so this approach, really supports that well. So what form does our MongoDB connectivity solution take? It takes the form of an ODBC and JDBC driver. That driver does contain a lightweight query engine in it, and that's the smarts, if you will, that knows how to take pieces of JSON data and map it into this relational form, these parent and child tables. Our driver interacts with the MongoDB cluster in a natural way using BSON. So BSON-based communications directly to the cluster. And MongoDB databases are exposed as relational schemas, which again is the most natural way to represent how MongoDB chooses to partition its data model and its collections into standards-based concepts. So let's just sort of hit quickly a little bit more detail about what the various normalization patterns. So there's a couple slides here with some examples of how to take various types or aspects or patterns of JSON and how you can choose to normalize it. And all of these examples were really assuming that these document snippets, these JSON snippets, are from a collection named employee. So in this case, we've got Brody again, that employee Brody with an address. And in this case, we've got an array of addresses. So the normalization pattern here would be to map that address array that's in the JSON document into a child table, and those array elements become rows in that employee addresses child table. However, you could choose to a different JSON pattern would be if the data model that you're shooting for with JSON here is such that an employee only has one address as opposed to multiple addresses, which is that first example. The approach here again would be to map that address, even though it's a single instance, it's not an array in this case, still into a virtual child table. So we've already seen a couple examples of this. So this is certainly a pattern or patterns that you see in JSON, and how you could choose to represent them in a normalized relational model using our driver. But you can, critically importantly, very importantly, JSON can be arbitrarily deep. I mean, the depth of a nested document and where a nested array can exist in a JSON document can go on and on and on. And in this example, we've got a case where there's an array of addresses, but each address instance in that array is itself a subdocument, a child JSON document, where there's different types of addresses, a home address or a work address. So this is an example of a deeper sort of JSON snippet, and this could as well be normalized into a child table where you've both flattened and you've normalized and flattened in the sense that that label, that home and work label, is part of this employee address child table along with the array instance address subdocument. And this can go on and on and on. And it's important to note that our solution here can can normalize arbitrarily deep arrays and arbitrarily deep documents in the JSON document in the MongoDB collection. So I sort of already mentioned it, but you can make choices about at what level you want to, what various levels of a JSON document you want to represent as child tables, but you can also make choices in our approach to flatten at a particular level. So to combine normalization with flattening, again, a lot of power in how to map the arbitrarily complex JSON document structure into a natural, stable relational contract. And in this case, we've got managers and nested managers. But we can map that into one single child table called employee manager. And sort of continuing on with that, here's another pattern of arrays nested within an embedded document. So I've got a subdocument, in this case manager, and that manager has multiple emails and represented as a JSON array, the emails array in this particular example. So again, this is an example where employee manager sort of represents both normalization and flattening, in that the emails have been mapped into the employee manager child table. So lots and lots of power, I think, is the real point here, and great flexibility in how you and your organizations make choices to bridge these worlds, connect these worlds of NoSQL to standards-based applications. And just sort of to wrap this up in terms of examples, here's an example of a real-life JSON document structure from a customer of ours that manages or represents store inventory, where you've got an inventory that consists of stores, an array of stores, names and locations and addresses. In this case, the address is a subdocument. And for each of those stores, there's an array of products, and there are departments and tags for those products. And each product has a set of SKUs describing the size or the color or the variety of the particular product. And how that would be potentially represented in a normalized model would be as an inventory stores parent table and an inventory stores product child table that sort of corresponds to that product level of the JSON document. And then another inventory stores products SKUs, and these names, you can control these names. These are just sort of example names here that are sort of directly connected with this particular example that contains the product SKUs. So inventory stores product SKUs relates to inventory stores products, and that table inventory stores products relates to inventory stores. So you've got this very natural denormalized, or rather normalized relational view that maps directly to the structure of the JSON document. And this can go on and on in terms of depth. So a lot of power. So, most of you will sort of be thinking at this point, well, how does this happen? MongoDB is schemaless. MongoDB doesn't provide you any metadata about what's stored in it. Where is this mapping? Where does that come from, and how is it used? And that's where the role of the schema tool comes in. There is to do this sort of normalized view or normalized mapping of arbitrarily deep to MongoDB does require some additional metadata. It does require some mapping metadata, and so there is a tool. You need a tool in order to capture that. And this is something you do once, right? Or you do once every time the structure of your JSON, your MongoDB collection changes, and you use the MongoDB schema tool. So this tool allows you to quickly and easily map and normalize that MongoDB schema. It samples the data in the MongoDB collection to present to you some information in order for you to make those decisions. It proposes data types based on that sampling that you can then choose to override. Because again, data in MongoDB is typeless. And SQL is a typed model, so there's some metadata required about what those types are going to be. And the schema tool provides a wizard that walks you through this either flattening or normalization process and gives you effectively a baseline from which you can then make choices about how to optimize your particular mapping. So as part of that sampling, this tool will present to you statistics about the data in the collection, data types, string lengths, the max string lengths that it found, min and max elements in an array in terms of numbers, so that you can make choices of, well, maybe this array is okay to flatten, and we will because that's the best choice in this situation. Or, oh, clearly we can't flatten that array because there's too much variety in the mins and max, or they're too far apart, so we want to map that array into a child table. So a lot of information for you to make those choices. But at the end of the day, this schema tool is about giving you the power to adjust and perfect that mapping and connect these worlds through setting types and sizes and altering column and table names, and maybe there are pieces of the JSON document that you want to hide or that you need to add from another level in the document. So what does that look like? And so here you see on the right-hand side an example or a screenshot of the MongoDB schema tool. From the left to the right, you've got on the left you've got, in this case, the standard ODBC data source definition dialogues. This is part of every ODBC driver. Things like what is the connection information to the data source in question in terms of where's it run and what port is it on and what's the database name, and in this case, where do I want to store that additional metadata that we're going to collect and use to map MongoDB into this relational world. That's the schema definition file. So on the right is the MongoDB schema tool. What you're seeing there is that it's presenting to you information about the data that it found in a collection, in this case the test database and the collections that are in the test database, MongoDB database. And you see information about the data elements that were found in terms of, in this case, columns, map names, and their potential SQL type, and their max lengths, and their ordinal position that you want them in the view. And when you click on a column, in this case the account ID column, you see some information about the statistics that the tool found and that the schema tool found in terms of sampling. So through all of this, you make choices about I want this column to be called this, and I really want it to be of this type, and that's possible based on the sampling that occurred and the actual data that's in the JSON collection, and you control really how this relational contract is constructed, and all of that information gets saved off into the schema definition file, and that's what really drives this normalization process. So what are some of the benefits of using this schema tool, this MongoDB, the DataDirect MongoDB schema tool, this mapping tool? Well, first, you use it to inject this metadata to create a stable relational schema contract to expose to applications that maps potentially complex MongoDB JSON data. As the JSON documents in a MongoDB collection evolve, because one of the powers and benefits of MongoDB is in fact its schemaless model, and MongoDB does not care. The JSON document instances that are stored in a MongoDB collection can change over time, and you don't have to do anything to MongoDB to allow that. Now, that isn't the most common pattern, but the point is that when that evolution changes from the MongoDB application, the application that's actually writing and storing data into MongoDB collections, when that change happens, you're not going to break all of your relational consumers, right? Because that relational contract has been defined and is stable until you go back in and use that schema tool to adjust that mapping. So it gives you control over opting into those changes. You connect these two worlds, but yet you have some decoupling between your relational consumers and the view that they see over that MongoDB data and the application that's physically writing into MongoDB. So you've got some decoupling and control there. Is a key benefit of this mapping approach. So JSON structure changes won't break your SQL application, right? That's ultimately the key benefit, and you then have control over when you want to expose those changes to that ecosystem of relational consumers. Excuse me. And that metadata that's collected is stored in a easily readable XML file that you can easily distribute to your relational client. So it's not it's not tucked away in some database instance that's difficult for you to then distribute to the various clients that need to consume relational clients that need to consume that MongoDB data. So I mentioned that MongoDB is schemaless. MongoDB doesn't even care and doesn't impose and doesn't restrict you from writing JSON documents into a collection that are potentially different than another document that's in that collection. So there's potentially a fair amount of inconsistency. So there's this notion JSON is effectively, because it's schemaless, or MongoDB and JSON, effectively because it's schemaless, is dynamic and can be dynamic. Now an application that's writing into MongoDB is going to be writing in a particular way, right? So the reality is that application is going to expect some particular JSON document structure, but the point is that MongoDB itself does not care. So what happens in the case where there is some differences in the document instances stored in a collection, in the sense that documents don't need to have the same set of data in them, or even the same structure, or that document to document fields that are in those common fields that are in those documents may hold different types of data. In one document instance, a data element might be an integer, and that same data element in the next document instance in the MongoDB collection could in fact be a string with non-numeric characters in it. So there is this potential for inconsistency in terms of how the data that's in the particular collection. So what is going to happen in this flattening and or normalization mapping, where we're, the relational world, the relational consumers are interacting with this schema definition, this view, and in returning or processing that data, we encounter some of these inconsistencies. How do we handle this? And so there's a set of policies for how that gets handled by our solution. And so mapped fields that perhaps are absent from a particular document resulting from a query against a MongoDB collection will result in a null value in the relational, the corresponding relational column for those relational consumers. And if there's additional data that's in that JSON document, that's just sort of a no-op, right? Because anything that isn't mapped to the relational view is not going to, isn't going to affect the relational consumers. What about these fields, though, with varying data types? So the driver is, going to attempt to apply that type definition that's defined in the schema using the schema tool. If the conversion fails, a null is going to be returned, and there's a set of effectively coercion policies to sort of force that type where possible. But if that conversion fails, because that coercion is not possible, then we will return a null along with an error message. So there's a policy for how we, again, connect these worlds in terms of how the normalized relational view that's exposed by our ODBC or JDBC drivers handle this potential inconsistency in NoSQL and in MongoDB in particular. So, the use case that is most prevalent in connecting these worlds of NoSQL to relational is a read-only use case. It's feeding MongoDB data to this ecosystem of consumers in your organization for querying or for analytics, right? MongoDB has a set of very specific proprietary developer APIs. So applications that are constructed directly to interact with MongoDB would typically use those APIs, and that's not a use case that we're really targeting here with this solution. But having mentioned that, and as part of that, the default behavior of our connectivity solutions to MongoDB is in fact read-only. But if there is a limited use case where one of those standards-based consumers, SQL consumers, does need to write something into MongoDB, we do support insert, update, and deletes to what are called JSON simple types. That is, data items that are at the root or parent level of the JSON document. So we do support insert, update, and delete to effectively the parent level of the document. And we do support create and drop local tables. Sort of temp tables, if you will. Tables that are not ultimately going to be persisted or backed in MongoDB, but are really stored in the driver's in-memory representation of that relational schema. So what isn't supported is insert, update, and delete into deep or nested portions of the JSON document. So the use case is read. That's really where the pain exists. But there are some edge cases that do require write capability, and we do support those edge cases, but into the top level of the document. So what are the key takeaways that I'd like you to leave our webinar today with? First, connecting these worlds, connecting the ecosystem of relational applications, such as analytics and BI tools, to the world of NoSQL and MongoDB, it's hard, and there's pain there. And the industry approach of flattening the complex information represented and stored in JSON or in NoSQL sources and in MongoDB in particular into this potentially very wide relational row just really isn't enough. It's insufficient. It isn't the way that the ecosystem of relational products wants to and expects to see that data. And what's needed is this more powerful approach to normalize, to give you choices and power in how to represent these potentially complex and deep MongoDB JSON documents into a natural, stable, normalized relational schema. So with that, for those of you who are making use of MongoDB or certainly are considering using MongoDB and have this pain of connecting the data in those systems to the rest of your standards-based products, your SQL products, we certainly would want to recommend taking a look at this at our solutions. So we provide a 15-day free evaluation at the URL that you see at the bottom of the screen. Quickly download it. Very simple form to fill out. Nothing too onerous. And in a couple minutes you'll have a evaluation license, and you can give our solution, including all of the power of our schema tool and the power of the normalization approach, a try against your particular MongoDB use case and JSON document structure. So with that, I will pass back to Marlis, our host,
Great.
for handling any questions that we've keyed up. And it looks like we have, a little bit of time left for that.
Yes, we do. And thank you so much, Brad. Let's see. Our first question that we have is, if the JSON structure is changed, the schema visible to SQL application, does it remain stable or do you have to change it? And a little bit of a follow-up. Is it possible to have many schemas accessible to the same MongoDB repository?
Well, those are good questions. So as we had sort of spoken and just sort of recapping that, if the underlying JSON document structure that's stored in a collection changes over time, those changes will be isolated from the SQL applications that consume that data. So that contract, that relational view really that you create with the schema tool, and that mapping of that relational view into a particular JSON structure is in fact stable, right? It won't automatically change if the JSON document structure that now gets stored into that collection begins to change. And that's one of those key benefits, right? You want to have that decoupling of your relational consumers and what they see from the potential change over time to what an application is physically writing into MongoDB. And that's a good thing, but there certainly is, if that JSON document structure is changing, it's getting written into MongoDB, it's likely that, in fact, you do want to expose that information to your relational consumers, and that's when you use the schema tool to opt into those changes. You go back into the schema tool looks through its sampling and compares it to the existing schema and says, oh, well, these things are different. It'll highlight them in yellow, and you can then say, yes, I do want to expose that, and it lives here. Or no, that's something that I don't think I'm ready to expose to my relational consumer, so I'm going to just ignore that change. So there's a control point there. And it certainly is possible that you can create multiple schema definitions to the same MongoDB database and to the same collection in a MongoDB database, and that different schema definition, that different view, can be used by different classes of relational consumers. So that is absolutely possible.
Brad, thank you so much for coming into the studio and presenting all this information with everyone today.
Thanks so much, Marlis.